Thanks to all of you who are here. This is going to be a very interesting interview and a wee bit different. This is going to be a highly technical interview. We've had some of those, and we've not lately, though. So my name is John Fasella. Many of you know me. I'm the past president of RCA as of almost 2 years ago now. And I'm also semi-retired, and so this is one of the things I still enjoy doing for RCA. We have Barney Scholl, who is our vice president and legal counsel for RCA, and Barney has been with RCA many years. And we have Dr. Robert Johnk, and Dr. Johnk is many things, life senior member of IEEE. He's done a whole lot of stuff. Basically, his entire career has been involved with propagation and predictions thereof. He's written 54 IEEE articles, 23 NTIA reports, and 17 NIST reports. And interestingly enough, where Bob worked is where we visited last year. It's too bad we didn't know you at that time, Dr. Johnk. But RCA each year holds this meeting in a different place. Last year it was in Boulder, and we visited the NIST laboratories, and we also went to WWV, which was interesting. So we've right in your neck of the woods. All right, without further ado, I think we're going to get started. Dr. Johnk, why don't you give us a short overview on your background and some of the areas of propagation that you work in, please?
Well, I had a very rich career. I got my PhD in electrical engineering in 1990 at the University of Colorado. I specialized in electromagnetics and antennas propagation. And shortly after that, I got a great opportunity to go work at NIST. I was almost on the verge of going to Ball Aerospace to work in their antenna group there, but I chose NIST instead. And looking back, it was a great decision. But when I got to NIST, I had this sort of naive notion that I was going to be an electromagnetics analyst and solve boundary value problems, look at antenna problems. And then when I got into NIST, it was hard reality. These people were deep into measurements, and that was really interesting stuff. I mean, these people are serious with measurements. They milk those measurement systems inside and out. And it quickly caught my fancy there. And I decided instead of being an electromagnetics analyst, I was going to embrace measurements. I went with the flow. And very interestingly, my career segued into a whole series of special tests that lasted for the 17 years that I was at NIST and then the 16 following years that I was IETS. So by a special test, what I mean by that is that a customer would come to us with specific needs, and what me and my team would do, or when I was a team member and also a project lead, is we would work with that customer and say, okay, what are your needs? What problem do you want solved? And we would architect a measurement to solve that problem and give them critical data that would impact the work they were doing. And that really became addictive. I said, this is really cool stuff. I mean, this is where I found my niche. You know, a lot of people spend a lot of time when you start your career finding your niche, but boy, I hit it right off the bat. And initially, what we did work with was ultra-wideband systems. Now, ultra-wideband systems were basically a really fast pulse generator combined with an oscilloscope, and we had transmitting and receiving antennas, and we had specialized antennas called TEM horns at the time. And they were using these horns to actually do reflectivity measurements off absorbers in anechoic chambers, because a lot of chamber manufacturers were very concerned about how well do your absorbers perform. So we used impulse measurements to do that. And this ultra wideband system was the very start of my career working with that. And then we started looking at network analyzer, which is basically a CW, step CW measurement system. It's in a box, has a transmitter and receiver in a box. You would connect up transmitting and receiving antennas, and we could do sort of the same stuff. But then we evolved that system and started doing aircraft measurements. And in fact, I'll talk a little bit about the pinnacle of my career at NIST is NASA came to us in 2000, some years after I started my career. They came to us in 2004, And this was in the wake of the Columbia disaster. If you remember that, what killed the Columbia space shuttle was there was a foam strike event during launch where a piece of foam hit the leading edge of the wing of the shuttle and punched a hole in it, and they were not aware of it. So NASA really, before they resumed the shuttle launches, they wanted to uh, actually, they were going to do night launches. Of course, you can't see foam strike events at night, but one of the problems they have if you shine these high-powered radars on the shuttle during a launch, their EMC engineers were saying that you would have main engine cutout because of electromagnetic interference. And this is not good because if you lose your main engine on the shuttle, yeah, you have your solid rocket boosters. You'll make it to Africa, but that's about it, but you won't make it to orbit. So they tasked our team to go down and say, we need electromagnetic shielding, RF shielding data for the space shuttle. And they didn't have any on record. They had no such data. And so they came to us, and within 6 months, we had to mobilize and develop a measurement technique and program. And we actually went down to Cape Canaveral with this system. And we went to the shuttle landing facility. This was a hangar, kind of like a Quonset hut, a big Quonset hut with a concrete floor. It was all metal. We actually did a series of reference measurements in that facility to make sure it was suitable for these measurements. And then they towed the Space Shuttle Endeavour all the way from the orbiting processing facility, and they towed it a few miles all the way to this facility. And we did measurements for 2 weeks straight and gave them an entire set of data. So that was one of these special tests that I was talking about. And then after that, we were tasked by the Boeing Aircraft Company. They were doing development of an electronics warfare platform based on the 767 jet. So what Boeing ended up doing was they rented a jet. Don't ask me why that, from Delta Airlines. And we spent 2 straight weeks in a hangar down at Hartsfield International Airport in Atlanta. And we did shielding measurements on this commercial jet. We actually we did the reference measurements much as we did in the shuttle effort, but we placed our receiving antenna in the avionics bay, the flight deck, passenger deck, and various compartments, cargo compartments within the jet. And we gave them a comprehensive set of data based on that hangar measurement. But that was another style of special test. And then we evolved this system. We had General Motors come to us with a problem. They have a big outdoor antenna range. They were having a lot of range-to-range variations in their radio measurements. So we took our system to Milford, Michigan, the General Motors test facility out there, and we deployed our network analyzer, our transmitting antennas, just as we did in the other efforts. This time we had a dual optical link architecture. And we explored that facility, and we were able to help them get their antenna placements correct so they could get good range-to-range repeatability. But that was an example of the NIST career that I had. I mean, and these are all special tests. And this was all data going to customers, impacting them and helping them with their problem. And nothing more satisfying than that. Halfway through my NIST career, about 17 years in, I got very interested in more traditional radio propagation measurements, and I transferred over to the Institute for Telecommunication Sciences in the same building. It's all under the U.S. Department of Commerce, and we're all descendants of the original Central Radio Propagation Lab. And I started doing mobile channel measurements. The Office of Spectrum Management was doing model development for their propagation models to understand source victim interference and wireless interference potential in their EMC studies. So we did a very rigorous mobile-to-mobile channel measurement campaign, where we actually had a fixed transmitter with antenna heights that were fairly low, about 1.5 meters. And we would have one vehicle with a fixed transmitter location. And then we would drive and set patterns on the streets, and we would measure propagation loss and delay spreads. We were actually using a PN channel sounder. This is what they call a pseudo-random noise generator. So wideband system, approximately 10 megahertz wide. It just sends out a chip, a random sequence, and you could use correlation methods to get an impulse response and get kind of more familiar time domain data, and we could extract propagation data from that. However, I had a lot of questions. It was a very sophisticated system. I really, when I looked at data, we had very sophisticated signal processing. I wasn't sure if that data was good or not. So I started doing CW measurements, where you send out a single tone, and then we used a spectrum analyzer to actually capture the waveform, and we could measure path loss directly doing that. And eventually I evolved it into a more sophisticated CW system using what they call a vector signal analyzer. It's a more sophisticated instrument, but basically it would capture that CW tone, but we could measure path loss very accurately and robustly with that system and measure Doppler spread. So that was part of it. But after several years at the institute, we suffered some big funding cuts, and that was a disappointment to me. When you're really gaining momentum, but we had some agency cuts, from Washington at the time. That happens. And so I approached Jeff Bratcher over at PSCR, and I said I'd really be interested in working in public safety. And he said, we have a problem for you to work on, and that was in building. And I spent the next 5 years, and I'll talk about this a little bit more after that, give you some more details on that. So I embarked on a 5-year adventure there. And I have to say, in my ITS career, that was probably the high point. I mean, that was a great program. PSCR, Jeff and Derek ran a great program, great managers. And plus, as a hard scientist, I was placed in close proximity to a bunch of people that they had hired from the wireless industry, places like Nokia, Ericsson, Motorola. So it put me in close proximity to really practical wireless engineers. So we had a pretty good synergy. They taught me a lot of things. I learned a ton from them. I think I taught them a few things as well about good measurements, but it was a really enjoyable time of my life. And then after that, we worked on some measurements. We took our early mobile channel measurements at the under the sponsorship of DARPA, and actually did underground measurements after that, after the PSCR wound down. And then I did some work on HF radios for Fort Huachuca, the Joint Interoperability Testing Command, JITC, because they had these advanced radios that they had no test procedures for. Of course, we had given up on HF in the early 2000s because we wanted to do HF at that time, but the military got really interested in it very, very fast, and so we had to learn quickly. So that was really something. So that's how my career progressed. And then I phased retired in 2021, and I still mentored for the last 2 years of my career younger engineers, teaching them a lot of these techniques and working with them. So that kind of gives you the span of my career and what I did. So, but
Well, that's
I'm 34 years on, looking back, I said, wow.
You've had quite a career, no question about it. So you mentioned, Dr. Johnk, you mentioned underground tunnels. Could you tell us a little bit about that and why this was important and some of your findings in various frequency ranges?
Yes, absolutely. In 2018, DARPA started this program called I think it was the SUB-T, the Subterranean Robot Challenge. And it was actually a contest. They invited teams to participate in this contest. And people were going to take underground robots into these different underground environments like coal mines, or I think this is where we did our measurements, but in mining environments. They did some work here in Colorado, also in eastern Pennsylvania. But part of this subterranean challenge is they would send these robots into underground environments, and you'd have to communicate with them. Okay, you would have a controller at some point, but you didn't want to send people into these disaster environments. You wanted to send these robots in, but you had to communicate with them. So DARPA came to us when I was at ITS and said, we really would like to see some radio propagation characteristics in some of these environments. Well, given their budgets and everything, we settled on the Center for Disease Control, the experimental coal mine in Brewston, Pennsylvania, about 21 miles south of Pittsburgh. They run a very large experimental mine where they do health and safety studies for miners and underground scenarios down there. They had about 50 experiments ongoing. And so we took our equipment out there, and we did some initial, tests with it, and did some scouting. And we came up with a mobility solution of mounting a CW transmitter on a cart with a fixed transmitter with some fairly sophisticated CW receiving equipment. And we did drive testing underground. And the ultimate result of this was we bundled a lot of data and ported it to DARPA so they could study it and better understand underground communications issues. But we did a full venue of not only CW measurements, but also pulse time domain measurements. And that's what they use that data for. So ultimately, they did actually have one of they had one of their robot contests in that exact mine. And the results were very, very interesting. So, but what we learned about tunnel propagation is that above tunnels were very much like a waveguide. Below a certain frequency, your radio signals will attenuate very rapidly, but you get above about 700 megahertz, you get very robust attenuation. You go higher in frequency, still robust, but you'll get multiple modes and you can get cancellation effects as you go down the tunnel. But when you go around corners, you lose a lot of signal with each corner that you go around. And that's one of the things that we saw. And so as a result, a lot of these robot teams that actually tested in that mine would either, one of them used tethered Ethernet, which is kind of a brute force solution to kind of have tethered cable going into that environment. I don't think that's ideal. Other systems, other contestants, I guess, evidently dropped these little breadcrumb transmitters, repeaters at selected intervals so they could communicate around these corners and down the tunnels. So that was the work there. And so I think I don't remember who the winner was, but this is all described in the April 2022 edition of IEEE Spectrum, not the radio side that we did, but the actual competition there. But to me, that was another high point in my ITS career, was doing underground measurements. We spent 4 days in that coal mine and we did 161 drive tests. And because we were careful with our measurements, we only had one bad data set out of those 161s. I thought we did really well.
Was there a particular frequency that propagated better than others?
No, I think as soon as you got above about 700 megahertz, I think as you got up towards in the Wi-Fi bands, 2.5 gigahertz probably was about optimal in that mine. They actually had an underground communication system in that mine that consisted of repeaters. I believe it transmitted in the, if I remember correctly, in the 900 megahertz band, the ISM band, if I remember correctly. But we saw that 2.5 gigahertz propagated better. Now, in preparation for this effort, again, we only had 3 months to mobilize. We had to, number one, get our equipment together. We did a lot of testing in underground utility tunnels at our laboratory. We actually had a long 1,700-foot long utility tunnel that we actually tested our ideas in before we went out east, but we carefully crafted and built that effort based on, we put our equipment on carts and did some careful testing. We carefully calibrated antennas, and we wanted to get to a point when we started the drive tests that when we measured signals, they're right where we needed them to be. And on several occasions, we found bad connectors and things in our tests before these drive tests commenced. So our preliminary preparation really paid off.
Okay, good. I'm going to jump ahead, Dr. Johnk, to what you did with wireless in-building in band 14 for FirstNet.
Okay.
So I understand there were two phases to your work, and the first phase was to quantify measurements, and the second phase was trying to find an app that could be used on an ordinary cell phone so that public safety users could do some level of measurement without a lot of sophisticated test equipment and training. So why don't we talk about phase one first?
Well, phase one basically, and there was really two phases to it. Yeah, the phase one lasted, I think, from 2012 to 2015, about 2.5 years. And when I started working with PSCR and Jeff, we started working with drive test equipment, much like actual cellular network testers would use. So one of the unique things that we had to work with that particular sequence is we actually had our own experimental band 14 network in the Boulder area during that period. It was under our control. It hadn't been taken over by AT&T at that point. So we were able to, it had two fixed E-node Bs in it in the Boulder area, and it also had we also had a cell on wheels where we could actually move it around to different locations, and we did early drive testing outdoors with it. For the in-building work, we used that network as well. And we went to this building. It's on the east side of the engineering center on the campus of the University of Colorado. It's called the Discovery Learning Center. It was a good building for testing because it's very representative of modern building architecture. It has the metallized glass. It's a LEED certified building. A lot of RF attenuation to it, which you'll encounter in a lot of these new buildings. So at any rate, we basically wanted to look at ways in phase one of enhancing in-building coverage. That was a major piece of it. So we ended up doing a lot of walk testing, and we had this funky backpack that we would put on. We would put in two devices. One was the device under test. It was an LTE modem, or dongle, as we would call it. You could use a phone, but we in those days used a dongle. It was an early Motorola prototype. We didn't have a lot of band 14 equipment in those days, and we used it in parallel with the scanner. A scanner is just a passive device, a passive receiver that would receive a lot of LTE parameters. It would collect data continuously. You didn't have to attach to the network. If you want to collect data from your dongle, on the other hand, you have to be attached to an eNode B to actually pass data and record it. And so I had a backpack combination and a laptop computer, and then we would load a floor plan on that computer, and we would take known navigation points on that floor plan. We would call these known navigation points breadcrumbs. And so we would walk test roughly at a constant rate. And then what it would do is once you pass these known navigation points, you would tap on the tablet, and then it would record the data. It would linearly interpolate the speed between points, and it gave some pretty good results. So we could do some really good geolocated data. And so I summarized that in a report. It was written in 2015, and I think I provided you the link to it. That was a 280-page report, but we did some extensive testing on the campus there with that. But to enhance the in-building coverage, we did two things. Once we took a single sector, well, there were three things actually. We took a cow, a cell on wheels, and wheeled it in close proximity to the engineering center, about 100 meters away, and beamed 40 watts right into the engineering center, just to see what sort of coverage we could get. Coverage was okay on upper floors, but when you got into the basement, it was poor. Even at 80 watts at point blank range, we were blasting that building. So we set up a small cell that one of the PSCR stakeholders provided. It was a 5-watt single sector small cell. It's basically a small eNode B, but it doesn't have 3 sectors, just one. We actually put discrete antennas in a classroom. We deployed it in a classroom in one of the buildings there. We actually had optical link connectivity back to the evolved packet core back in the Boulder Labs, our central nervous system of our LTE system. And we were able to control it from there. And we did walk testing with that, and we found that that greatly enhanced the in-building coverage. We also sponsored a student project at the Interdisciplinary Telecommunications Program at the University of Colorado. And we had 3 students design a DAS system, which is a network of cables and antennas you would install in the season. It's called DAS, Distributed Antenna System. It was a passive DAS. And they actually put, I think, 3 or 4 points around the perimeter of one of the floors of the Discovery Learning Center. And we did coverage studies of that, and it greatly improved performance too, but it interlinked with our other systems. We actually had different combinations of the cell on wheels, the discrete antennas with the small cell. We had the DAS going. We looked at different combinations of coverage and did a thorough study. And so we did that, and we also did a similar study over at the Coors Event Center in a different environment. It's a large stadium at the University of Colorado where the basketball team plays. They have graduations. They give final exams. We actually installed a small cell in the upper ceiling area of the Coors Event Center, and we did that for illumination, did extensive walk testing there. But at the end of the day, we had really good data for in-building, but afterwards, the public safety folks said, boy, this is complicated, because this equipment did take a lot of training to operate. It took me at least 4 months to master the walk testing and really get repeatable, good results. And in fact, I gave a talk at APCO, and somebody came up to me, and afterwards, it was a special session, I think Derek was chairing, came up to me and held up an Android phone at me and says, look, I can do this on a phone. Why do you need to do this, sort of measurement? Why do you need to use this sort of equipment? Well, that was a good point, but I said there's a little bit more to it than that. It's not quite as simple as you may think, but it was a good point. And so the idea started to percolate. We started talking about it and said, look, let's make this type of measurement accessible to public safety practitioners. So we developed our own app at PSCR. We actually had a really good app developer, Joe Parks, who was my ITS colleague at the time, was a really good app developer, really good with Java programming. He was really hot with that stuff. I was just an E&M guy, I was not into that, but I was into measurements. But he developed that app, and we actually installed it on the Android devices. Now, PSCR at the time, because FirstNet was going to go with Android devices, we developed it for Android devices, and it is available. But at any rate, what you would do is just, it would record what we call reference signal receive power. RSRP is it's called. And the nice thing about RSRP, number one, it gives you a signal level metric, and it doesn't change with the level of traffic on the network. If you go with another parameter, let's say RSSI, that will change with the level of traffic on the network. So we went with our SRP. We felt that that was a good steady metric. And of course, these systems actually use our SRP for handover decisions and and also signal recording. There are other parameters you could use, but and another note too, we didn't go to some other data rates and things like that, or bit error rates, because we wanted to keep the measurement procedure simple. We didn't want to encumber the operator with having to initiate data flows, because that gets complicated. I wanted to be able to train a public safety officer in the space of 10 minutes to do their own measurement. And the whole concept was, if you do these measurements yourself, first of all, we're not gonna do these sophisticated geolocation mapping and everything. What we would do is you would walk a zone of a building, say a hallway or an auditorium or something, or a specified pattern in a building. It would take all of these RSRP measurements and compress them into a score between 1 and 10, where 1 was the worst coverage, 10 was the best. And we had 3 categories. Score between 1 and 4 was poor, 4 to 7 was good, and then 7 to 10 was excellent. And so they could go in and press this button on the app and do their walk testing. And in fact, this app would give you the ability to pause the measurement, and then you could resume it in a different part of the room. And then it would record the data. It would give you a final number, a coverage score. We also had a pie chart that it would display showing you the percentages of good, excellent, and poor measurements. And it would also store it on a CSV file and on a phone, all of that data, so you could do additional post-processing with it. But we let police officers do it. We did some inter-comparisons, like on the campus of the University of Colorado, and we let them operate this phone, and we also had our experts run the same tests. And at the end of the day, we couldn't tell the difference between what the police officers got and what we got with that device. So that was
Okay.
really satisfying.
So we have some slides. We don't usually show slides, but we have a few. Do you want to go through them real quick, Dr.
Yeah,
John?
I could do that. Yeah, I kind of described it there. I'll step through it. How much time, John, would you say would be comfortable
We,
for you? A few
we
minutes?
well, yeah, we have I would say about 5 to 8 minutes.
Sure. I'd be happy to step through those very quickly.
Screen.
Just to
Okay.
give you a little bit more of the flavor of what I've described verbally here.
Are you seeing the screen?
Yes, I am.
Okay. Just tell me which slide you want right now.
Okay, you can go ahead and step to slide 1. And oh no, we can keep going. Let's go ahead and go to slide 4 here. So we'll skip the underground measurements at this point. And then we'll keep going. You want to go there. Okay. This sort of shows the 2 phases that I described already. Let's continue on to slide 6. This is a map of the Boulder, Colorado area. If you look at the yellow lines there, if you look at the very bottom of the map where the little marks are, that's there's an E-node B located on Green Mountain just above the Boulder Labs. If you look at the next annotation up from that, that's the Discovery Learning Center. And if you go way up to the top of the ramp, that's our next E-node B that's located on our Table Mountain test site about 8 miles north of Boulder. But that's a general map of the Boulder area. Right near where the center annotation is the Discovery Learning Center, and then the Boulder Commerce Labs are towards the bottom. But that gave you that was our experimental network that was operational for 5 years, actually longer than that when I was involved with it for 5 years. But very valuable resource. We don't have that anymore, but that was a unique opportunity. Next slide. And here's a picture of the Green Mountain E-node B here that was up on the Kohler Mesa above the Boulder Labs here. If you look at the upper left-hand picture there, if you look at the shorter of the 2 antennas, you can see the panel antennas there. That was a 3-sector E-node B. And actually our stakeholders installed their equipment in that metal building right next to it. We had like Ericsson and Nokia E-node Bs in there at the time. And we could actually run those and do our experiments with them. If you go to the right-hand picture there, this gives you kind of the proximity of the E-node B to our Boulder Laboratory main radio building right there. It was about 1 kilometer away. Gives you some of the flavor of that. And we did a lot. If you look at that at the end of the arrow, at the bottom end of the arrow there, that is the Precision Measurement Laboratory, the PML as they call it. And we did a lot of our early testing in there. This was the Physical Measurement Lab, Precision Measurement Laboratory at NIST. And it was a great place to test. Next slide. So at any rate, here's some pictures of the Discovery Learning Center. The left-hand picture, you can see the cell on wheels there. One of the sectors was active, beaming energy into the nearest wall of the Discovery Learning Center there. And here's a picture on the right-hand side of the cell on wheels there. We only had one sector active during these testings, but the idea was to improve building penetration. Next slide. Here's an actual small cell here. If you look at the bottom center photograph, it's on the back of the cabinet there. That's a small cell, an LTE small cell. That one was built by Nippon Electric Company, NEC. They were one of our stakeholders. Ran 5 watts, one sector. You can see it was 2 antennas for full MIMO. We had stick antennas, if you look at the left-hand graph there, that illuminated the building from within there. That was interior illumination. If you go to the right-hand graph, that was the control panel and the network connection that went back to the Boulder Labs and the Evolved Packet Core there, and we could control all of that. Next slide. And here's a picture of the DAS project here. This was the ITP, worked in conjunction with Professor Ken Baker, who was a professor at the time. We had a group of 3 students doing a student project designing DAS. In fact, Ken Baker taught a course in DAS for a Maymester. I actually took that class to learn more about DAS systems. But on the left-hand side, you can see the left-hand upper photograph there, you can see the small cell feeding this DAS system. If you go down one picture there, this was the passive DAS system. It consisted of the antennas in the ceiling, cables, couplers, and all passive components there. If you look to the right-hand side, you can see one of the DAS installations, two antennas. You go all the way to the right next to the fluorescent fixture there at the base. You can see the 2 DAS antennas right there. And they were designed to transmit about 200 milliwatts within that hallway. We had 3 or 4 different locations around that hallway. And they, as their student project, we studied the improvement of coverage. One delightful thing about working with students is that, when you're supporting them, the university had no problem with us installing a DAS in their building. We didn't have to get any special permissions or anything. They just said, do your thing, take it down when you're done, and we're okay with it. Now, if you were an outside wireless provider, you might have more difficulties there, but working with the university provided some great opportunities. Next slide. And I think this is the backpack system I was talking about here. This is what I did the interior walk testing. There's a picture of what I looked like in 2013. I did look younger in those days, but here I'm actually the upper left-hand photo there. You can see the laptop computer. It was a tablet. And it had the drive test software. This software was not cheap, by the way. This is specialized drive test, but it would pull LTE parameters. If you go further down, we had an LTE dongle. It would pull dongle data off through USB connections. If you look to the right on the other side of the backpack, we had a front and back compartment. We had the LTE scanner in the back, and we would collect data in parallel. So that's how we did that. So if you go to the next slide. Here's an idea, here's what I've plotted here was sort of a histogram. It has count on the vertical axis, it has reference signal receive power on the horizontal axis as a function in dBm. But you can see if you only had the cow only, this was on the first floor of the Discovery Learning Center, you can see the range of powers that you receive with just the external cow blasting energy in there. As soon as you lit up that small cell inside the building, you notice your signal levels improve dramatically. So this is an example of what interior support could do for you. That was pretty cool stuff. Next. And then we segued into phase 2, and you can continue on. But here's a listing here, by the way, John, of here's some links to these the LTE app and which I'm going to discuss shortly, and that report that I described. Next. And this was the experimental app interface here. You can download this from Google Play even today. If you want to run it, you need to configure a phone to, receive LTE, and you can do that. I can do that with my secret codes on my Samsung S24. It's not a problem. And maybe other vendors, you have different procedures. But here you would actually get you get your disclaimer, and then you could just simply had a very simple set of menus, and it just gives you kind of an idea of how this app works. And you can see at the bottom of the slide there, you can see the pie chart, and you can see the percentage that are good, excellent, and poor coverage. And the right chart, you can get a line chart as well. You can get a time series of those RSRP measurements from your measurement campaign there. And to the right here, we actually have the phone, the right-hand picture. We have a phone mounted on an antenna mast, and this particular monopole here, this fed a LTE scanner on a cart we used as a reference system. Go ahead and change slides here real quickly. And here's a picture of the actual reference system that we use. So we place the phone on this cart. We had a monopole antenna that we characterized numerically, and it fed into the LTE scanner. We had a power supply, and then we would push this cart with these two devices, the scanner and the phone, in parallel. So we would have a reference. We would have a reference measurements. Now, if you look in the 3GPP standard, these phones, not all phones are the same. If you look at the specifications in the 3GPP standards on our SRP measurements, they have a plus or minus 8 dB variation from phone to phone. That's what the vendors can have. So you can have as much as a 40-to-1 difference in power measurements with phones from one phone to another. And not only that, if you were doing it in voltage, it would be about 7-to-1, 6-to-1 in voltage. So we use this reference system because these phones had a lot of variation between them. These are not designed to be precision measurement systems, as we quickly found out. Next slide. And here's a picture, actually, if you look at the left-hand slide, this is actually a geolocated map of the physical measurement lab I showed you in an earlier picture. Here's actually a signal map of our SRP, where you see blue and green, you have high signal levels. The actual signal was coming from the external E node B from the left hand of the graph. But when you got into the deep interior, see those red areas, they're very weak signals in there. And what we experienced, if you look over on the graphs to the right, we did some multiple tests there. This is just one example of it. The black trace is what you get out of the scanner. It's continuously getting data all the time. But when you use the phone as a measurement device, notice you see these flat spots on the bottom of the graph. That's where the phone loses connectivity with the E node B. You lose lock. And then as the signal gets stronger, you recover that. So that was another issue. So next. And we also looked at body effects with these phones. Here's 3 different ways that we held the phone. The first one, we used a selfie stick to hold the phone on the left-hand photo there. Looks like an aging RF engineer. That's myself, aging even more now since those measurements. We held it in the hand in the middle. And then in the right-hand graph, we had it in the pocket. So if you go to the next slide, here's the impact of that, what happens there. We have a plot here of coverage score. This is called a box and whisker plot. These little boxes here with these little whiskers on top and bottom are minimum, maximum coverage scores. This was the result of 6 repeated measurements. The little red line is called the median. But notice as you go from a selfie stick, you get a good coverage score. But as you get more body effects kicking in, notice that your coverage drops in the hand. And then you get to the pocket, you lose signal. Yeah, your coverage score is degrading because that's the absorption effects of the human body. So what we recommended public safety practitioners to get consistent measurements, use a selfie stick. This was for scuba diving. It is available commercially. Get a little body separation. And what we found was that was exactly equivalent to what we were getting on the cart. So that was good enough. So finally, let's go to the next page. Here's some measurements we used the University of Colorado police officer to do measurements in conjunction with our engineering team. This was at the Champion Center in Boulder, Colorado, home of the Colorado Buffaloes. Hopefully they'll have a better season this year. That's another story. But we did very detailed measurements. And if you go to the next slide, you can actually see Officer Donna of the Colorado Public Safety actually using a selfie stick in the left-hand slide and then putting it in her cargo pocket and doing prescribed walk tests around the Champion Center there to check coverage. And they were very concerned about that because they'd had a shooting at the university around that time, and they were very interested in building communications because there had been a shooting at the time, and they were very, very supportive of it. And okay, one more slide, and I think that would wrap it up. We also went to or actually a couple more, the George R. Brown Convention Center down at Harris County, Houston. Harris County actually had an experimental LTE network at the time, public safety network, 40 E node Bs in Houston. And we did extensive measurements in the center. It's a huge center, about a half a kilometer long. We did actually on that day 13.5 miles of walk testing. It was a good power workout. If we didn't get anything else out of it, we were in pretty good shape. Next slide. And they actually had a DAS system inside the George R. Brown Center. That's the DAS antenna that they could turn on and off. So we could do intercomparative tests with the DAS turned on and off. And they were very cooperative. They agreed to turn the DAS off at request. And again, very supportive of this work. Next slide. And we also had our engineering there. That's Jason Kane from NIST pushing the cart there in the George Brown Center with the test phone and our scanner. And there was a Harris County public safety officer there doing measurements with a selfie stick too. Once again, our statistics showed there was no difference between the experts and the public safety practitioners. And I think that's it for the deck.
Okay, so what I'm going to do is, Barney, are you there?
Yes.
Yeah, I think it's time to open it up to audience questions, but I'm going to leave up this particular slide for a little while because it has where to pick up Dr. Jonk's document and the LTE app. So, Barney, why don't you take over and
A
start
few
with some
a,
questions?
a few questions have popped up here. Going, I'll say backwards or forwards. I'm curious as to why you concentrate on Android devices when about 60% of all public safety people use Apple devices. I can understand doing both, but concentrating on Android devices seem to ignore the facts of what a large segment of public safety users.
Well, that's an excellent question. I mean, I didn't make the policy on that, but I think it's a really well posed question. I think there was discussion of making an Apple version of that app. 10 years ago, they were telling us we're going to be doing Android devices. This was in the early days of FirstNet during its formulation and in the work that we were doing uh, in that area. And by the way, I wanted to point out too, just to let everybody know, this work was funded by the Department of Homeland Security, not FirstNet, and I just wanted to make that clear. But going on to that, we were basically directed to work with Android devices. I wasn't clear on the policy reasoning behind it at the time, but that's what we were told, and that's where we focused. And again, I would have to talk to the policy people and why they made that decision. I don't know why they did that.
Okay. Next question, I'll mention it. This one comes from Professor Jim Breakhall. You mentioned about HF and the increased interest in it. Can you discuss some of the projects you worked on in HF? And then he
Yeah,
also commented, he said he was presently working himself on different next generations HF projects for the Air Force, Army, Navies, and Navy.
yes, that's a really good question. In fact, not until the very end of my career did I get to work in HF, although I've been a ham for many, many years and worked in HF there. But we were approached by the Joint Interoperability and Testing Command, JITC, from Fort Huachuca. They were getting these new fourth generation HF radios down there. And what JITC does is they have to do conformance testing to standards of these radios. And they had no test procedures at all. They had procedures for 2G systems, a little bit on third generation systems. Now this is different from cellular. This is an evolution of HF technologies, and this is more related to data rates, automatic link establishment. It's totally unrelated to the cellular world. But they had no test procedures, and of course, all of our HF capabilities had atrophied in the early 2000s. Who cared about HF? I mean, we were doing LTE, FirstNet stuff, and DHS research at the time. Nobody cared about HF, and then all of a sudden, somebody in DoD finally recognized, oh crap, what happens if we lose our satellites? What if we're internet denied? How do we communicate? Oh, gee, we need some HF here. And so that was one of the drivers. And in fact, almost simultaneously to that, we were approached by there was a great big meeting down at the U.S. Air Force Academy. I also got approached by I worked with DHS on a HF field demonstration, all in 2018. All of this kind of came down at the same time. That people said, "Oh crap, what happens if we can't, if we lose all of our incumbent networks and satellite capabilities?" Yeah, HF was kind of the driver. So what we ended up doing was we worked with HF. I mean, we worked with Fort Huachuca folks. They actually got us a 4G radio, and we developed a whole series of conformance testing to look at not only the digital communication side of things and capturing data and precise testing procedures that you had to go down. We had a team of about 6 people working on it. We came up with a 400-page document, but we also looked at automatic link establishment, and these radios were very advanced. You could transmit data at 250 kilobits per second, bandwidths up to 48 kilohertz. These were pretty revolutionary radios. They had no test procedures, so we developed that. We were caught pretty much flat-footed on that, but we responded as best we could, and they seemed pretty happy with the work that we did. But that was the only HF project that I worked on.
Okay, thank you. A comment here, a version of this talk might be good at the Dayton Hamvention. That was thrown out as a thought. I was thinking one myself. You've discussed working in the HF all the way up to the much higher frequencies. How does your work Are there unique characteristics that affect measurements as the wavelength changes drastically?
Well, I think, that's an interesting question. I mean, higher frequency measurements typically are harder to do. Lower frequency measurements were not as difficult to do. I think one of the challenges that we faced with HF radio testing was we had to actually craft instrumentation suites and everything to measure the parameters they were looking for. We really had very little guidance on it. We did get some training from one of the 4G radio manufacturers. They actually showed us how to use the radio and stuff, but we had to kind of go back and look at old standards and kind of figure out how things were going. So that was very tedious. But in terms of the actual measurements, once we crafted them and figured them out, it was pretty straightforward to do them. The only complicating factor with the HF project was COVID hit us at the same time. And we remember 2020, that was a wonderful year. It shut our labs down almost entirely. So we could only have one person go into the lab at a time, which does slow down an effort, by the way. However, we were able to work with remote testing capabilities. We had a Linux system, and we did actually some secure remote access to the radios. And most of my radio tests were done reading the old standards and doing control from the basement of my house using this remote network. So that was one of the unique challenges there. So that was hard, but and it was very stressful. It would have been nice if we'd had the team on site to do all of this, but we had to work with what we had.
A question popped up here. Did you do any experiments with wideband and/or spread spectrum testing?
Well, in fact, yes, there has been spread spectrum testing at the Institute. I did not, but we did have. Well, the PN channel sounders that we were using to do propagation measurements were spread spectrum. I mean, you were using PN sequences to actually spread spectrum out to roughly 10 megahertz wide. So in that sense, we did those types of spread spectrum measurements using for propagation purposes. I never did any actual radio, spread spectrum radio system testing.
One a little bit more personal. Understand that you are involved in Army Mars. How much time do you spend in a month as a Mars operations?
I love Mars. Well, Mars is a really cool program. I mean, if you're a licensed ham, you can join. You have to really disciplined net operations. Basically, the whole concept of Mars is the design of Mars is to operate in a satellite denied, internet denied environment, and we communicate exclusively by with HF radio. We do it with two modes. One is automatic link establishment, where we have a network of message centers around the country, and we can actually use ALE, automatic link establishment, to link up to those message centers and pass information to it. Or we operate in directed nets, and we coordinate those directed nets by voice, and then we pass data using encrypted, the mil standard 110A format. And we do different types of messages like road conditions, fuel availability, weather reports, airport conditions. I mean, we give all of that information. It's a one-way information flow from the station to Netcom down in Fort Huachuca. What I really enjoy about it is you operate on HF channels that are in between the ham bands, and I've learned a lot about radio propagation with that. That's one of the aspects of it. I really also enjoyed the really disciplined nets. We keep it very short, professional. We learn how to run efficient nets where we pass information quickly. If we encounter really terrible band conditions, kind of like what we did with the solar flare last month, we have to do propagation checks, find channels, reconstruct the net, and pass information. So it is a lot of fun. I find it very challenging. And plus, I do a lot of ionospheric simulations too. When I see these weird conditions, I try to simulate them, try to understand what is going on here. And so it is a lot of fun. I've really enjoyed that. And I've been involved with it for 2 years. I probably spend about 2 hours a day on it. And I've neglected my ham hobby a little bit because of it, but it is sort of an extension of that.
It is. Moving on, that leads me into another question. What are the very simplest sites to direct younger people ages 8 to 18 to learn and understand propagation? In their opinion, many experts are more about demonstrating their intellect rather than making it understandable.
I know how you feel. I feel your pain. How about that? That's a really good question. I would suggest, I mean, YouTube is a tremendous resource. There's just gazillions of propagation presentations. I think Dr. Tamitha Scoff, she does a really good series of ionospheric lectures, and I think she keeps it really kind of low key. But I would look at that, and I would also explore other YouTube channels where, you know, radio propagation, introduction to radio propagation. There's a ton of material out there. I would just suggest you look at some of those channels. Nothing comes to mind other than Dr. Tamitha Scoff. She's really good. I really like her presentations on the solar conditions. But there's a ton of stuff out there on, you know, the ionosphere and at a basic level that I think you could understand. And they talk about some of the programs like our ITS VOACAP, you know, these ionospheric prediction tools. They also have some ray tracing stuff that you can get out there. But if you want to learn it at a fundamental level, I would suggest exploring YouTube and just kind of watch them. And if you know you don't want to have any of that, just go to another YouTube and until you find something you like that's satisfying.
Another question directed towards younger people. What thoughts would you pass on to younger engineers and technicians just starting in wireless?
Well, I mean, one of the first pieces of advice is, you know, make yourself smarter. What I mean by that is you want to master, certainly if you want your basic tools, you want to know electromagnetic theory if you can. Learn as much about E&M and antennas. Learn about communication theory to the extent that you can. Also, if you're working in a workplace, find a mentor. Find a senior engineer you can work with that'll explain things to you. That'll help a lot. And I would also encourage you also to get training if you have training opportunities in your workplace. To you know they'll have these short courses that last a week or something. You know, take training courses, take advantage of opportunities there. If you want to take classes at the university occasionally, I would recommend it. But you know, keep your saw sharp and you know keep and also read a lot. And I also encourage you to document what you do. I mean, if you can publish, a lot of people can't. But if you can document what you're doing, keep careful notes. That's another thing that I would advise you to do is document what you do. And also embrace every project you work on as a learning opportunity. And if you do it enough times, you'll soon become a subject matter expert. You'd be surprised. The other thing I also wanted to mention was also, you know, be patient with yourself and also, you know, approach your career with humility and look at it as a learning opportunity. You approach it with humility and also be very, you know, persevere. If you suffer setbacks, keep looking forward and keep attacking the problem until you get it. That's my advice. You know, don't let setbacks, and there will be a lot of them in the course of your career. I've suffered a lot of them. You just simply look forward and you overcome them. So I would really encourage you to do that. But those are some of the things that I would advise young people to do.
Good advice, I'm sure. Question came up. Have you considered participating in the HAM Citizen Science Project?
You know, oh, go ahead. Sorry.
No.
That was the question.
Yeah.
I saw some presentations. I went on a tour you were mentioning earlier. I think, John, that you'd seen WWV. I went on a tour last March. This was before I retired about a year ago, about 3 weeks before I retired. And there were some good presentations on the Citizen Ham Radio Project. And I would be very interested. I have a lot of interest in propagation, software-defined radio. Yeah, I would be interested in participating in that.
And I'm sure they are always looking for more volunteers to help with the program, from what I understand. Another question is, has there been any research on the biological effects non-thermal of non-ionization radiation? I understand several years ago there was some research by others at Colorado Boulder.
Probably at the campus when I was at NIST and NTIA, that was such a hot political issue. We didn't touch it with a 10-foot pole. However, because yeah, it was very controversial. Most of the work that I was aware of was Department of Health at the time, and I knew some Silverberg. I'm trying to remember his name in the EMC Society. He did a lot of work in biologics, and in the Department of Health, there's a lot of that research. At NIST, they did not want us to get anywhere. They didn't even want us commenting on health effects of electromagnetic waves. It was just a political thing, and we were instructed not to do that. But it is an important area, and I was trained in some bioelectromagnetics in terms of I got some training, took some courses, but I was never able to do anything with it. So there you go.
Another comment here that I popped up by Ham's side. They comment they gathered 57 million data points from the April 24 total eclipse, solar eclipse QSO party. So that was a comment that was thrown out.
Wow.
Then a question from Al N7WYE. He appreciates your time presenting on DAS to building systems, as most legacy systems are in VHF, UHF, and 7 to 900 megs. Can you speak to vexing propagation issues in these bands?
In building, is that your understanding?
I think so. He didn't specifically say that.
It
And
just it depends on the type of building you're working in, the structure of the building. I mean, you can get vexing problems at VHF. VHF, in fact, if you go down these hallways, oftentimes you'll be below cutoff in many of these buildings, and they'll attenuate very rapidly. You may find in certain situations that, you say you do 150 megahertz in building, or let's say a 2 meter, 145 megahertz signal in a building, you'll find it'll very rapidly attenuate. But you go up to 800, 900 megahertz and it propagates a lot better. There's a lot of complex issues that go on in building, and they are vexing because it varies from building to building, architecture to architecture. There's no set rule for it. You just have to understand, study the structure of the building, and you can kind of infer perhaps where the good propagation possibilities are. But oftentimes lower frequencies are not good.
well, John, I've run out of questions, I believe, that have popped up. I think I've caught them all.
You have. I have one last question for you, Dr. Johnk.
Yeah.
You went into some detail about the testing in building. Was there anything for FirstNet? Was there anything anomalous or unexpected in what you saw in all that testing?
Yeah, I guess if I were going to rank it at the top, the most unexpected thing was as I showed you that reference measurement system where you had the monopole and the phone, and, we were looking at the differences between them. We never got consistent differences. The differences between a phone and the monopole would change from venue to venue. For instance, if we were in the Coors Event Center in the University of Colorado in a narrow hallway, we might see an 8 dB offset between the scanner and the phone. When we went into the open stadium area, that was reduced to about 2 dB. And what we found was, what we concluded is that these offsets were just very much a function of the electromagnetic field structure in these buildings, and there was no consistency. We had hoped that we could do a simple correction factor that would correct our phone measurements to the scanner, so that way we could get really consistent precision measurements. But that one went by the wayside. So that was probably the biggest anomaly, and kind of, it was a little bit of a bummer. But on the other hand, if you install the app on the phone that the practitioners are using, you're fine. But you can't get precision measurements. That was a little bit of a disappointment.
Understood. Thank you. Well, Dr. Johnk, this has been great. This has been a highly technical and a somewhat different session with the slides. A couple of things I want to tell the audience. We'll be doing another one of these interviews in September. It'll be Tuesday, September 10th. And then we have one final interview for the year, which will be in December. For those of you that plan to attend RCA's annual event, it will be in New York City this year. We're planning a number of interesting tours on both Thursday and Friday. So think about coming early. Of course, the banquet and the technical symposium will be on Saturday. But we have these tours, and you're really going to like them. I'm actually working on them myself. Mm-hmm. Also, APCO is coming up soon in Orlando. It's the first week in August. On Monday, there will be an RCA reception at some kind of Italian place. Imagine that. And I hope that everybody is enjoying these interviews. Please tell your friends and colleagues at work They're free, and this will be video archived in about a week or so. So you'll be able to look at it again. And if there's anybody that missed it, they can look at it at their leisure. Thank you all very much. Thank you, Dr. Johnk. Thank you, Barney, and good luck to all. Have a good week.
Well, thank you very much for the opportunity. It was an honor. And thank you for all the folks in the audience with your good questions. I really appreciate it. Feel free to contact me if you have any further questions.
Okay, great. And somebody did ask for the PowerPoint slides. We will make them available when we make the video available. All right. Thank you, everybody. Take care.
Thank you, John, Barney.